The concept of Nemesis as a hypothetical twin star of the Sun is an interesting idea that has been proposed in the field of astronomy. According to this hypothesis, Nemesis would be in orbit within the Milky Way galaxy and would approach the Sun at regular intervals of around 26 million years. It has been suggested that the gravitational influence of Nemesis could potentially disturb the outer regions of the solar system, causing comets or asteroids to be redirected towards Earth. One of the significant aspects connected to Nemesis is the possibility that its gravitational forces could have played a role in mass extinctions on Earth, including the demise of the dinosaurs. The proposed scenario suggests that Nemesis' gravitational influence might have disrupted the Oort cloud, a distant region of the solar system containing countless icy objects. The disruption could also have caused one or more comets or asteroids to be dislodged from their orbits and sent hurtling towards Earth, resulting in catastrophic impacts. The impact event that is commonly associated with the extinction of the dinosaurs occurred roughly 66 million years ago, and it left behind a massive impact crater in the Yucatan Peninsula, also known as Chicxulub Crater. It is suggested that a large celestial object, possibly influenced by Nemesis, collided with Earth, causing widespread devastation and triggering a series of events that led to the extinction of the dinosaurs and many other species. The proposed connection between Nemesis and the unusual orbits of certain objects in the outer solar system, such as Sedna and V774104, is another aspect worth considering. Sedna, discovered in 2003, was the farthest known object in the solar system at the time, and V774104 held that distinction in 2015. The wide orbits of these objects have raised questions about their origins and gravitational interactions. It has been speculated that the gravitational pull of Nemesis could explain these unusual orbits, although further research is needed to confirm or refute this hypothesis. The study of the Perseus stellar nursery provided intriguing insights into the formation of stars. Researchers scrutinized the stars in this region and employed statistical models to analyze their behavior. These investigations revealed a pattern. Stars like our Sun tended to form in pairs or even multiple systems. This finding suggests that our Sun may have initially shared its birth with a companion star. Within these stellar pairs, these stars are thought to form at a distance of around 500 astronomical units, where 1 astronomical unit is the average distance between the Earth and the Sun. To put this into perspective, 500 astronomical units is approximately 17 times the distance from Earth to Neptune, the furthest planet in our solar system. Over time, these star pairs may either break free from each other or gradually draw closer together. Identifying our Sun's twin among the vast number of stars in the galaxy poses a significant challenge. These statistical models provide insights into the likelihood of the existence of a twin star, but pinpointing the specific counterpart remains elusive. Therefore, the exact nature and location of Nemesis, if it indeed exists, remains an open question. A compelling aspect of the Nemesis theory revolves around the possibility that the twin star went supernova shortly after its formation. When a star is born, it primarily consists of hydrogen, which undergoes nuclear fusion to produce helium. As the star ages, it consumes its hydrogen fuel until it depletes, causing it to utilize helium as its new source of energy. This process continues until the star exhausts all of its fuel, ultimately leading to the fusion of elements and the production of heavier elements like iron. However, elements beyond iron on the periodic table can only be synthesized during a supernova explosion. These catastrophic events generate immense energy and heat, enabling the creation of elements such as gold, uranium, and other heavy elements. Therefore, the presence of these elements on Earth suggests that they were formed during a supernova explosion. If the Nemesis star existed as the twin companion to our Sun, its demise as a supernova would have dispersed these elements into space. Over time, gravitational forces and other celestial processes could have allowed some of these elements to coalesce, forming planetary bodies like Earth. This intriguing proposition implies that the planets within our solar system, including Earth itself, may be remnants of the death of the twin star. The idea of a failed star is a term used informally to describe objects like Jupiter and other gas giants that are similar in composition but don't have enough mass to sustain nuclear fusion like a true star. While Jupiter and the gas giants in our solar system share similarities with stars, they are fundamentally different in terms of their formation and behavior. Stars, including our Sun, are formed from the gravitational collapse of massive clouds of gas and dust, primarily composed of hydrogen and helium. As the core of a protostar grows denser and hotter, it eventually reaches a critical point, where nuclear fusion ignites, releasing vast amounts of energy. This fusion process generates the intense heat and light that make stars shine. Jupiter, on the other hand, is a gas giant planet composed mainly of hydrogen and helium, similar to a star in terms of its elemental makeup. However, it lacks the necessary mass to initiate and sustain the nuclear fusion reactions that define a star. Instead, Jupiter radiates primarily the heat it has retained from its formation, as well as some internal heat generated by gravitational compression. EBLM J055557AB is indeed one of the smallest stars discovered in our galaxy. It has a radius slightly smaller than that of Saturn, which makes it smaller than Jupiter. However, it is still much more massive than Jupiter and is capable of sustaining nuclear fusion in its core, unlike gas giants. While it is possible that there are other stars similar in size to, or even smaller than Jupiter, they would still need to have sufficient mass to sustain fusion in their cores to be classified as stars. Gas giants like Jupiter and other exoplanets discovered so far fall into the category of planets rather than failed stars. Another theory for the comets rather than a star is Tyche, a gas giant planet that is hidden in the Oort cloud. Tyche was hypothesized in 1999 to explain why comets tend to cluster rather than disperse randomly. Tyche is a hypothetical gas giant planet proposed to exist in outer regions of our solar system, specifically in the Oort cloud. The Oort cloud is a theoretical cloud of icy bodies that is believed to surround the solar system at a considerable distance. The hypothesis of Tyche was put forward in 1999 to explain the clustering of comets rather than their random dispersal. However, it is important to note that the Oort cloud itself has not been directly observed or proven to exist. It is based on mathematical models and indirect evidence. Therefore, the existence of Tyche is purely speculative at this point, and there is currently no concrete scientific evidence to support its presence. While the idea of Tyche is intriguing, further research and observational evidence would be required to establish its existence. While Tyche is based on the idea of a gas giant planet in the Oort cloud whose existence has not been proven, the ninth planet theory stems from the search for a larger planet beyond Neptune to explain the orbital behavior of certain TNOs. Both theories require additional evidence and research to establish their validity. That's all for today. Don't forget to like, subscribe, and hit that notification bell icon to stay updated on all our mind-blowing content. And if you have any theories or suggestions for future explorations, drop them in the comments below.